Redi-Volt surge suppressors sold by enerTECH claim to provide surge protection and reduce power bills by 20%. However, there's no evidence to support these claims. A previous discussion on the MikeHolt website also found enerTECH's claims to be not credible. It is important to be cautious about these devices as there is no scientific evidence to back them up. Investing in a reputable surge protector from a well-known brand is recommended. Surge protection is a critical aspect of electrical system design, safeguarding sensitive equipment from voltage spikes and transients that can cause damage, downtime, and financial losses. Traditional surge protection devices, or SPDs, operate by diverting excess voltage to ground, thereby clamping the voltage level and preventing it from reaching connected equipment. These devices typically utilize components such as metal oxide varistors, or MOS, silicon avalanche diodes, or SADs, and gas discharge tubes, or GDTs, to achieve this diversion. The effectiveness of an SPD depends on several factors, including its clamping voltage, surge current capacity, response time, and the quality of its grounding system. A lower clamping voltage provides better protection by limiting the voltage surge to a lower level. Higher surge current capacity allows the SPD to handle larger surges without failing. Faster response time ensures that the SPD can react quickly to transient events. A good grounding system is essential for providing a low impedance path for the surge current to flow to ground. When evaluating surge protection solutions, it is important to consider the specific needs of the application. Different types of equipment require different levels of protection, and the severity of the surge environment can vary depending on the location and power grid conditions. For example, sensitive electronic equipment such as computers, servers, and medical devices require more robust surge protection than less sensitive equipment such as lighting fixtures or appliances. In areas with frequent lightning strikes or power grid disturbances, a higher level of surge protection is necessary. Several types of SPD are available, each with its own advantages and disadvantages. Firstly, there are Type 1 SPD, which are installed at the service entrance of a building to protect the entire electrical system. Secondly, Type 2 SPD are installed at distribution panels or subpanels to protect branch circuits. Thirdly, Type 3 SPD are installed at the point of use, such as at an outlet or directly connected to equipment. Selecting the appropriate type of SPD depends on the level of protection required and the location of the equipment being protected. Remove the most common type of surge protection component. They are voltage-dependent resistors that exhibit a high resistance at normal operating voltages and a low resistance at high surge voltages. When a surge occurs, the MOV rapidly switches to a low resistance state, diverting the surge current to ground. MOV are relatively inexpensive and offer good surge protection performance. However, they have a limited lifespan and can degrade over time due to repeated surges. SAD are semiconductor devices that offer faster response times and longer lifespans compared to MOV. They are typically used in sensitive electronic equipment where fast and reliable surge protection is required. However, SAD are more expensive than MOV and have lower surge current capacity. GDT are gas-filled tubes that provide high surge current capacity and low capacitance. They are typically used in Type 1 SPD at the service entrance of a building. GDT have a slower response time compared to MOV and SAD, but they can handle very large surges without failing. Proper installation and maintenance of SPD are essential for ensuring their effectiveness. SPD should be installed by a qualified electrician in accordance with applicable electrical codes and standards. The grounding system should be properly installed and maintained to provide a low impedance path for the surge current to flow to ground. SPD should be inspected regularly for signs of damage or degradation and replaced as needed. In addition to surge protection, power quality is another important consideration for electrical system design. Power quality refers to the characteristics of the voltage and current waveforms in an electrical system. Poor power quality can lead to equipment malfunctions, downtime, and increased energy costs. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Voltage sags are momentary decreases in voltage that can cause equipment to malfunction or shut down. Voltage swells are momentary increases in voltage that can damage sensitive equipment. Harmonics are distortions in the voltage and current waveforms that can cause overheating, increased energy losses, and equipment failure. Transients are short-duration, high-voltage spikes that can damage sensitive equipment. Power quality problems can be caused by a variety of factors, including nonlinear loads, switching events, and lightning strikes. Nonlinear loads, such as electronic ballasts, variable frequency drives, and computers, draw current in a non-sinusoidal manner, which can generate harmonics. Switching events, such as starting and stopping large motors or switching capacitor banks, can cause voltage sags and swells. Lightning strikes can induce high-voltage transients in electrical systems. Several solutions are available for mitigating power quality problems. Firstly, harmonic filters can be used to reduce the levels of harmonics in an electrical system. Secondly, voltage regulators can be used to stabilize the voltage and prevent voltage sags and swells. Thirdly, surge suppressors can be used to protect equipment from transients. Fourthly, uninterruptible power supplies, or UPSs, can be used to provide backup power in the event of a power outage. When selecting power quality solutions, it is important to consider the specific needs of the application and the severity of the power quality problems. A power quality audit can be conducted to identify and quantify power quality problems. The audit will involve measuring voltage, current, harmonics, and transients at various locations in the electrical system. The results of the audit can be used to develop a plan for mitigating power quality problems. Power factor correction is another important aspect of power quality management. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the electrical power is being wasted. Power factor correction involves adding capacitors to the electrical system to improve the power factor. Improving the power factor can reduce energy costs, increase the capacity of the electrical system, and improve voltage regulation. Capacitors store electrical energy and release it back into the system when needed. By providing this reactive power, capacitors reduce the amount of reactive power that the utility must supply, which improves the power factor. Power factor correction is typically implemented at the distribution panel or at individual loads. The amount of capacitance required depends on the load profile and the desired power factor. Power factor correction can be a cost-effective way to improve power quality and reduce energy costs. However, it is important to select the appropriate type and size of capacitors for the application. Overcorrection can lead to voltage instability and other power quality problems. A qualified electrician should be consulted to determine the appropriate power factor correction strategy. Electrical codes and standards provide guidance on the design, installation, and maintenance of electrical systems. These codes and standards are developed by organizations such as the National Fire Protection Association, or NFPA, the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. The National Electrical Code, or NEC, is the most widely adopted electrical code in the United States. It provides comprehensive requirements for the safe installation of electrical wiring and equipment. The NEC is updated every 3 years to reflect changes in technology and industry practices. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It also includes specific requirements for different types of occupancies, such as residential, commercial, and industrial. Compliance with the NEC is essential for ensuring the safety of electrical systems and protecting people and property from electrical hazards. In addition to the NEC, other electrical standards provide guidance on specific aspects of electrical system design and operation. IEE standards cover topics such as power quality, grounding, and surge protection. ANSI standards cover topics such as electrical safety and equipment performance. Staying up to date on the latest electrical codes and standards is essential for electrical engineers, contractors, and inspectors. These codes and standards provide a framework for designing, installing, and maintaining safe and reliable electrical systems. Proper grounding is a critical aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which allows overcurrent protection devices to trip and clear at the fault. A properly grounded electrical system reduces the risk of electric shock and minimizes the potential for fire. The NEC specifies detailed requirements for grounding electrical systems. It requires that all metal enclosures, such as equipment cabinets and conduit, be grounded. It also requires that the neutral conductor be grounded at the service entrance. The grounding electrode system typically consists of a ground rod, a ground ring, or a metal water pipe. The grounding electrode system should be connected to the grounding busbar in the service entrance panel. The size of the grounding conductors depends on the size of the service entrance conductors. The NEC provides tables that specify the minimum size of grounding conductors. Ground fault circuit interrupters, or GFCIs, are another important safety device. GFCIs protect people from electric shock by monitoring the current flowing in the circuit. If the GFCI detects a difference of 5 mA or more between the current flowing to and from the load, it will trip and interrupt the circuit. GFCIs are required in wet locations such as bathrooms, kitchens, and outdoor areas. They are also required in construction sites and other hazardous locations. Arc fault circuit interrupters, or RFCIs, are another type of circuit breaker that protects against electrical fires. RFCIs detect arc faults, which are dangerous electrical discharges that can occur when insulation is damaged or wires are loose. When an RFCI detects an arc fault, it will trip and interrupt the circuit, preventing a fire from starting. RFCIs are required in bedrooms and other areas where arc faults are more likely to occur. Electrical safety training is essential for all workers who work with or around electricity. Training should cover topics such as electrical hazards, safe work practices, and the use of personal protective equipment, or PPE. Workers should be trained to recognize and avoid electrical hazards. They should also be trained to use safe work practices, such as de-energizing equipment before working on it and using lockout/tagout procedures to prevent accidental energization. PPE, such as rubber gloves, safety glasses, and insulated tools, should be used to protect workers from electrical hazards. Regular safety meetings should be held to reinforce safety training and to discuss any new hazards or safety concerns. A comprehensive electrical safety program should be implemented to ensure the safety of workers and the public. The program should include written procedures, training, and regular inspections. The program should be reviewed and updated regularly to reflect changes in technology and industry practices. Electrical maintenance is essential for ensuring the reliability and safety of electrical systems. Regular maintenance can prevent equipment failures, reduce downtime, and extend the life of electrical equipment. Electrical maintenance should include visual inspections, testing, and cleaning. Visual inspection should be performed to identify any signs of damage or deterioration. Testing should be performed to verify the performance of electrical equipment. Cleaning should be performed to remove dirt, dust, and debris from electrical equipment. Thermography is a valuable tool for electrical maintenance. Thermography uses infrared cameras to detect hotspots in electrical equipment. Hotspots can indicate loose connections, overloaded circuits, or failing components. Thermography can be used to identify potential problems before they lead to equipment failures. Power quality monitoring is another important aspect of electrical maintenance. Power quality monitoring involves measuring voltage, current, harmonics, and transients in the electrical system. Power quality monitoring can be used to identify power quality problems and to track the effectiveness of power quality solutions. A comprehensive electrical maintenance program should be implemented to ensure the reliability and safety of electrical systems. The program should include written procedures, training, and regular inspections. The program should be reviewed and updated regularly to reflect changes in technology and industry practices. Energy efficiency is an increasingly important consideration for electrical system design. Energy-efficient electrical systems can reduce energy costs, conserve natural resources, and reduce greenhouse gas emissions. Several strategies can be used to improve the energy efficiency of electrical systems. Firstly, energy-efficient lighting can be used to reduce lighting energy consumption. Secondly, energy-efficient motors can be used to reduce motor energy consumption. Thirdly, variable frequency drives, or VFDs, can be used to control the speed of motors and reduce energy consumption. Fourthly, power factor correction can be used to improve the power factor and reduce energy losses. Fifthly, energy management systems, or ENZs, can be used to monitor and control energy consumption. Energy-efficient lighting can reduce lighting energy consumption by up to 75%. LED lighting is the most energy-efficient type of lighting. LED lighting also has a longer lifespan than traditional lighting, which reduces maintenance costs. Energy-efficient motors can reduce motor energy consumption by up to 50%. Premium efficiency motors are designed to operate at higher efficiencies than standard motors. VFD can control the speed of motors and reduce energy consumption by up to 60%. VFD are typically used in applications where the motor load varies over time, such as pumps, fans, and compressors. Power factor correction can improve the power factor and reduce energy losses by up to 10%. Power factor correction is typically implemented at the distribution panel or at individual loads. EMS can monitor and control energy consumption throughout a facility. EMS can be used to identify energy waste and to implement energy-saving strategies. A comprehensive energy efficiency program should be implemented to reduce energy consumption and costs. The program should include energy audits, energy-efficient equipment upgrades, and employee training. The program should be reviewed and updated regularly to reflect changes in technology and industry practices. Surge protection, power quality, electrical safety, electrical maintenance, and energy efficiency are all important considerations for electrical system design. By addressing these considerations, electrical systems can be designed to be safe, reliable, and energy efficient.